I want to take this as an opportunity to quickly review things that we went over and some common mistakes people tend to make in this class. So on the blackboard, this is my version, like a simplistic version of the equation sheet you might think about, right? So keep in mind that whenever we write out equations, we want to know what exactly is the situation these equations are applicable for, right? So for example, in chapter 1, we went over the ideal gas law. Remember, the ideal gas law is an equation of state describing the relationship of your pressure, volume, and temperature. We derived the ideal gas law from the Charles law and the Boyle's law, which are two experimental observations. Now, when we're dealing with an ideal gas, or say the gas molecules doesn't have any volume, they don't interact with each other, these are only true for ideal gases. In the problem that didn't specify the system being an ideal gas, you're not supposed to use these laws. That means like PV equals nRT, or internal energy of the ideal gas is only dependent on temperature. It doesn't change with respect to volume or pressure if we keep the temperature the same. Now, the origin of this equation rooted back in statistical mechanics that we will cover in later section. But for now, just accept that for ideal gases, internal energy is only dependent on temperature. But nevertheless, just keep in mind when we're using these equations, these are only applicable for ideal gases. They're not applicable for like real gas or liquid or solid. All right. And to take it one step further, later when we talk about the first law of thermodynamics, we have the equation of delta U equals to Q plus W, or du equals to dQ plus dW. What that means is that for the first law of thermodynamics to be true, we are setting it to be a closed system at rest and no external field. So remember, the original version of the first law of thermodynamics is delta E equals to Q plus W. And this total energy equals to kinetic energy plus potential energy. Unfortunately, potential energy is also a V, but this one is potential energy. And plus internal energy, right? So internal energy is everything. It's a part of the energy. So everything that's not kinetic, that's not potential, that's our internal energy, right? So in the setup here, when we say the system is at rest, we're saying the kinetic energy equals to 0. No external field, we're saying the potential energy equals to 0. All right, so know where these equations comes from and know what situation you can use them for. That's important in this class. And then later on, well, actually before the first law of thermodynamics, we also went over the reversible PV work. So remember the work reversible, and whenever we say reversible, we're referring to like a super slow process, right? Any small infinitesimal change will put the system to its original state. So for reversible PV work, you get W reversible equals to negative PdV. And later on, at the end of our last lecture, we define a new state function, which is enthalpy. Now notice that in each cases, we have like something like to say like, hey, this is only true for reversible PV work. This is only true for closed system, etc. But these kind of definition, they're just generally true. Its enthalpy is by definition equals to internal energy plus PV. All right, so know where these equations come from and know when to use it. So that's why I highly recommend you come up with your own equation sheet as our class proceeds. Like try to write out these equations, and you can also add like a sample question, like for example, in this case, we specified ideal gas. That's why we're using these equations. So that's just a quick review of what we have covered so far. Okay, so for today's lecture, we have two main goals. I'm pretty sure I'm only gonna be able to finish heat capacity. So we will be focusing on heat capacity for now. In our next lecture, we'll be talking about the Joule-Thomson experiment, which gives us a mean to measure, to get an idea about how your volume or pressure change with respect to temperature by setting the total internal energy or enthalpy at constant. So these I'll save for next lecture because I'm 99% sure we can't finish it. Okay, let's get started on heat capacities. So first part of heat capacity, we will spend some time talking about what are heat capacity. To give heat capacity a slightly more accurate definition using terms of thermodynamics, now we know what is heat, what is temperature, etc. And then we will look at some math problems talking about how to calculate the heat capacity or what are the things we need in order to calculate heat capacity. And then we want to work out a relationship between the different types of heat capacity we covered. So getting started on what is heat capacity. So the definition of the heat capacity states that for any infinitesimal process, so we're stating that to be any infinitesimal process as like abbreviation PR in a closed system. So heat capacity is defined in a closed system for like infinitesimal changes, or CPR equals to the change of the infinitesimal change of heat with respect to temperature. All right, so this small abbreviation, PR, stands for any process of interest. Typically, in chemistry or in thermodynamics, we care about either isobaric process or isochoric process. So heat capacity is generally defined for any process of interest, but in this class, we will focus on isobaric heat capacity and also isochoric heat capacity. Remember, when we say isobaric, what we're saying is pressure is kept constant. And hence, we then remove this PR into little p, so that subscription P tells us that's the isobaric heat capacity or heat capacity measured at constant pressure. And Cp is defined as the infinitesimal change of heat at constant pressure over temperature. And recall at the end of our last lecture, we gave enthalpy a physical meaning. And the physical meaning of our enthalpy for any system, closed system, undergoes only reversible PV work. Our delta H equals to QP, or we can say the infinitesimal change of H equals to infinitesimal change of dQP. All right. Or the other way to put it, our Cp thus equals to dH over dt. Or to be more precise, since we're keeping pressure as a constant, we want to write it as a partial derivative of enthalpy over temperature at constant pressure. All right, so far in this case, what we did is only using, enthalpy and set pressure as constant with this closed system, PV work, and equilibrium. So these are the assumptions we made deriving this equation. Next up, we have the isochoric heat capacity, or in this case, remember what is isochoric? Which one is set constant for a isochoric process? Volume, right? So this is a constant volume. Now, like what we had before for a constant volume process, we then write the little subscription V, stating it is a constant volume process, and we have this dQV here. Now, in this case, what is the nature of this dQV? Remember, we have closed system, reversible PV work only, so we can use our first law of thermodynamics, so du equals to dq plus dw. So that's our first law of thermodynamics. And we're gonna drop like at rest and no external field from now because like in this class, unless we specify there's acceleration, which we probably want, or external field, let's just assume for the rest of this class, like it's always at rest and no external field. But in this case, we can use our first law of thermodynamics, so du equals to dq plus dw. Since we only have equilibrium, since we're at equilibrium or only reversible work is allowed, this dw term thus becomes negative pdv. Right, so we're using the equations on the board that we covered before. Now, in this case, it's isochoric. So volume is not changing. My dV is 0. Right, so volume is kept constant. So what we have is our dQV effectively equals to our du. Or we can rewrite CV as the partial derivative of internal energy over temperature at constant volume. So the rest of this course, we will be using these relationships more pretty often because they are generally true as long as we have a closed system, reversible PV work only. All right. So before we move on, I want to ask you a question here. Now we have the physical meaning of our heat capacity, right? So our Cp is the rate of change of enthalpy with respect to temperature at constant pressure. Our Cv is the heat capacity, is the rate of change of internal energy with respect to temperature at constant volume. So I want you to think about it. Whether or not my heat capacity, Cp and Cv, are they extensive or intensive properties? Remember the definition of extensive versus intensive, right? So an extensive property will be proportionally increasing as the amount of substance increase, while the intensive property will remain the same. Like density remain the same for a smaller box and a bigger box of milk, but the mass will be increasing. So in this case, are they intensive or extensive? So raise your hand if you think they're intensive properties. Okay, raise your hand if you think it's extensive property. Okay, so you want to explain why you think it's extensive? I can also do it if you don't want. People who vote for extensive. So in this case, the logic behind it is we're talking about the change of energy. So let me ask you one more question. My enthalpy and internal energy, are they intensive or extensive properties? Extensive, right? So in this case, because my enthalpy and internal energy are extensive properties, their rate of change with respect to temperature must also be an extensive property. All right. But we have intensive versions of the heat capacity that we have seen before. For example, if we divide our heat capacity with the number of moles, we got molar heat capacity, and this molar heat capacity will then become intensive property. Likewise, the specific heat capacities that we've seen before, these are heat capacities divided by mass. They are like smaller c. These are also intensive properties. Okay, any questions before we move on to do some example problems together? We're all clear? Yes. Yes, it is extensive. So heat capacities themselves are extensive, but molar heat capacity and specific heat capacities are intensive properties. this is pretty straightforward. You have cups of water, right? They contain, well, let's not use water. Let's use ideal gas. Now, ideal gas, you have like a larger cylinder of ideal gas. You have smaller cylinder of ideal gas. And the amount of energy in those cylinders depends on their size. So for ideal gases, I'm not sure if you cover that in your general chemistry, like the internal energy for a monoatomic ideal gas is like 1.5 nR, right? So you have the N in there in the equation of the internal energy. We'll go over more in statistical mechanics in that domain. Okay, so let's move on and see how do we use the definition of our heat capacities to actually solve, or actually to use these definition and also giving you relationships and expressions of internal energy and see how can we solve for heat capacities by doing some math together. So this is a simple question. Let's say we have a hypothetical material. We don't know what exactly is that material. The internal energy of that substance equals to, say, AN TP squared plus N times BT plus beta P third minus PB. All right, so can you use calculus and also definition of the heat capacities to solve for CP and CV? If you think it is not solvable, please state like why it is not solvable. So just to put the equations we're going to use is Cp equals to partial derivative of enthalpy over temperature at constant P. Cv equals to partial derivative of internal energy over T at constant V. So I'll give you a few minutes to work on it. I'll also be writing on the board, and then we'll discuss our results together. I'll keep these equations here for your reference, and you can replace it with your own equation sheet. I'll be working on Cp first, and then Cv. Can people in the back see my handwriting? It's going to be pretty small. I apologize. My handwriting just pretty small on the board. Okay. So this first part should be a pretty straightforward calculus problem, right? So what we have, we start by looking at what is Cp. That's a partial derivative of H over T at constant P. So we want to write out an expression for enthalpy. So reading the question together, we have an expression for internal energy, and we know enthalpy is by definition U plus PV. So we have H equals to AN TP squared plus N times BT plus beta P to the third. And that's just solving this derivative with respect to temperature. The first term is very straightforward, just the temperature goes out. And then the second one, you want to use a little bit of technique, like say X equals to PT plus beta P, and then do dx over dt. And there's lots of symbols, but the fact is this derivative should be a pretty straightforward one. Yes?
Should there be a 3?
Yes, there should be a 3. Thank you. All right. But what about CB? Any of you have any clue about whether or not we can solve for CB? Or you feel like you're getting there, you just need more time? So in this case, when we're looking at the expression of CB, now using U, which is like ANTP squared plus blah, 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 let's just focus on this first term. So what we want to have an expression of, say, this ANTP squared over temperature at constant volume. Right? Although we know volume, pressure, and temperature are interconnected using the equation of state, but in this case, there are things we do not know. Like we have no idea how pressure is dependent on, it's going to change with respect to temperature. Like for example, this term, like dP over, or dP squared, I guess, at constant V, that's something we just don't know, right? We have no idea how pressure is going to change with respect to temperature at constant volume. So by simply observing the equation, we can say that, hey, we do not have enough information. What kind of information do we need so we can solve this integral? Or we need an equation of state in order to help us solving for the derivative here to get an expression of CV. So this is a good example I want to highlight because it shows you that in this class, occasionally you'll be looking at this kind of expression, you'll be jumping too fast in trying to solve for the calculus. But you might want to slow down before you jump into the calculus. Just think about it. Do I have enough information to solve this problem, right? Don't spend too much time like simplify it and get stuck inside, wait, I don't know what dP over dt is, so we don't have enough information. And also in the drafting of the question, occasionally we will ask you, do you have enough information to solve for blah, blah property? If not, tell us what do you need to solve that. Okay, how are we doing on this one? Doing good? Yes?
I thought about like maybe we can write like P in terms of V. I don't know if that would help.
Right, exactly. So in order to write P as a function of V and T, we need the equation of state. Like for example, in this question, if I tell you this is an ideal gas, and then it becomes solvable because we have a relationship or we have a mean to write P as a function of T and V. Right now we don't know. We just don't. Yeah, it's not given in the question. That's the whole point. All right, so let's move on to our second example problem, which is deriving the relationship between CP and CV. So this one, we're trying to solve for a expression for CP minus CV, using the definition of CP and CV and also enthalpy. So we'll do it in two different fashions. The first one, we will solve for a general expression of CP minus CV using only calculus and then the definition of CP or expression of CP, CV, and also definition of enthalpy. All right, so using them only, we will get a more general expression for the term CP minus CV. And then we'll try to apply that general relationship into a special situation, which is an ideal gas. So let's work on that first. So first step, very straightforward. We're just writing down the definition, the expression for Cp and Cv, using the definition of enthalpy to plug that in. And since we're talking about constant pressure, this dPV term, you can take the pressure out because pressure is set to be constant. And then we have this expression of Cp minus Cv equals the partial derivative of U over T at constant P plus pressure times dV over dt at constant P minus du over dt at constant V. All right, so we get this first expression by simply writing out the definition of terms and what we know, the expression of Cp and Cv. The next one, we want to focus on these two terms here. So what do we have? We have two partial derivatives of internal energy with respect to temperature at constant pressure and volume. And at the same time, we know that temperature, pressure, and volume are interconnected with each other with equation of state. So my internal energy, U, is only a function of, pressure or volume, pressure or temperature, or volume or temperature. So it's only a dependence. It's only dependent on two out of the three properties because those three properties are interconnected with each other. With me so far on that logic? So in that case, let's just say we know that U is a function of temperature and volume. So you can try the same kind of calculation using temperature and pressure. Mathematically, it should give you the same result. Now, we're just set to say internal energy is a function of temperature and volume. We can write out the total differential of this internal energy, which is basically any function with two variables. You can write out its total differential. So that is, du equals to partial derivative of u over t at constant v dt plus partial derivative of u over v at constant t dv. We want du over dt. So in this case, I'm just going to divide both ends by dt. So we got du over dt on the left, and here everything else stays the same. So what we end up, du over dt equals to partial derivative of u over t at constant v plus partial derivative of u over v at constant t dv dt. All right, so these are the total differentials. Now let's focusing on the constant pressure process, or manually set pressure as a constant because in our original relationship, we have pressure kept as constant. So what we end up getting is du over dt at constant p equals to du over dt at constant v plus du over dv at constant t dv over dt at constant p. So we get an expression of the partial derivative of u over t at constant p using the following relationship. This part is only calculus. There is like nothing else going on. And then what we're doing is plug this entire thing back into that original equation. And if we look at it, so these two terms will cancel out. And this one is the partial derivative of v over t at constant p. This is the same. So we end up having the relation as, well, p plus this one, du over dv at constant p times my dv over dt at constant p. Or the other way to put it is we have a general expression on the relationship between my isochoric heat capacity and the isobaric heat capacity. Or in general, so my Cp minus Cv will equal to partial derivative of u over v at constant t plus p times partial derivative of v over t at constant p. So in this case, in this relationship, there is one thing here that we're talking about the partial derivative of our internal energy over volume. If we think about the dimensionality of this term here, on the top, we have joule or Newton meter, and on the bottom, we have meters third, right? So this one has the same dimensionality as pressure. So it's a very nice sanity check to make sure that, okay, we are plusing two terms or plus or minus two terms that have the same dimensionality. And this term here, later we will refer it as internal pressure. Okay, how are we doing here? So the two things connecting my relationship between my Cp and Cv, what we need are internal pressure and also the equation of state. So this one is the more like general version of the relationship between my Cp and Cv. These are my heat capacities. Now, using this general equation that we derived, we can apply it to a specific system of interest so we can solve for the difference between Cp and Cv. So a simple question might be the following. Now, like given Cv of an ideal gas is, say, 5 nR. Just quite randomly picking. Now, what is the Cp of this ideal gas? That's just a random question that I've dreamed about, right? So how do we solve for this question? So in this case, again, what we have is the general expression that we just derived to be Cp minus Cv equals to partial derivative of U over V, our internal pressure, at constant T plus P times dV over dt at constant P. Right, so for an ideal gas, what are the information we know? First of all, the internal energy, or internal pressure for ideal gas is 0. As we were saying, the internal energy of an ideal gas is only dependent on temperature. So this term is 0, so for ideal gas. This term is 0, so we can cross that out. This term, we have a main to solve it. We know that V equals to an RT over P, and thus this term becomes NR over P. Right, so what we can solve for ideal gas is that Cp minus Cv equals to NR. Or plug it back to the relationship we got, is that the Cv, knowing the Cv of the ideal gas is 5nR, the Cp of that ideal gas must be 6nR. So variations of this kind of problem might be, now we give you a different internal pressure and a different equation of state. Can you solve for the difference for Cv and Cp? Okay, any questions? All right, if we don't have any questions, since I didn't go over the next section in my 9 a.m. session, I want to use this time to do an example question to you, because one of you folks bring it up to me during office hour yesterday, and I found it pretty interesting. I want to share it with everyone. So let's do this one together. I'm gonna open a new note for it. So this is a question related to the nature of heat as a path integral. So we want to read it together. So can you explain how liquid water, just any kind of liquid water, like a cup of liquid water, can go from 25 degrees Celsius and 1 atm to 30 degrees Celsius and 1 atm in a process that our heat transfer is negative? All right, so this one is more like thinking about what exactly does it mean when we say define a process so it can happen in which heat is negative. Or what we can do is write out an initial state, say 25 degrees Celsius, And while pressure is the same, I'm just going to leave it out. And final state. (30 degrees Celsius).
There's something wrong with your display. That's it.
Oh, I never see that happen. Let's see. Okay, now it's better. Okay, and what we want is we want to have a process, or we want to define a process where Q is negative. Anyone want to take a guess or have some clue? The little hint is we will be using our first law of thermodynamics. So our first law of thermodynamics tells us like our delta U equals to Q plus W. And another piece of information to think about, when we have a cup of water, we put it in a container somehow. And then we are doing work on that cup of water. The way we do the work on that cup of water, you can imagine to have a magnetic star bar that's part of the system, but it has the same temperature, right? So there's no heat transfer. So that star bar can start really, really, really fast and do work on my cup of water and make my cup of water's temperature increase. All right, so the way to think about it is in this kind of question, it didn't specify anything. So we can use our thermodynamic knowledge to think about processes it can take place. Now, the way I set it up, you can imagine other pathways as well. This is just how I think about it, is we can have a container. Now, in this process, I put my water in there and a star bar in there, right? So that's my initial state. My water is at 25 degrees Celsius, 1 atm, as what the problem said. In addition, I manually add that my wall is adiabatic. That's my star bar. All right, that's something you can build. Now, in the intermediate state between my initial and final state, you can imagine to have my star bar doing work on the water. Now, when my star bar is doing work on the water, the whole process is adiabatic. So work is positive. My Q equals to 0. So Q equals to 0 tells us my system is separated with the surrounding by an adiabatic wall, so no heat transfer can take place. But my star bar is continuously doing work on my system, so the temperature must go up. All right, so what that tells us is eventually we will end up having the same box of water, the same star bar in there, the same adiabatic wall. But the temperature of the water must go up because my star bar is continuously doing work on the system. Now let's say my temperature is raised to 100 degrees Celsius or 98. Let's avoid the problem of evaporation, just to make my life easier. Right, so the first process, do we get it? Like the temperature can increase while keeping Q as a 0, adiabatic. And then the second step becomes, now let's remove the adiabatic wall. I don't have to remove everything, just remove like part of it. And I put my star bar at rest. It's no longer doing work on the system. So my second process, my work equals to 0. But now my temperature need to drop in order to reach that 30 degrees Celsius. So the second step, my Q must be a negative number. All right, so this is one of the questions that by first reading it, you'll be like, this is very counterintuitive. My temperature is going up. How can heat being a negative number? But the fact is, in thermodynamics, as long as we can define a pathway to go from A to B, from state A to state B, we really, it is possible to define such a pathway so the heat transfer is a negative number. Your textbook has a little bit more extensive, extended reading on this topic, saying like how exactly that takes place. I'm pretty sure it's in this chapter of first law of thermodynamics. So this one is just a interesting question. I think I should bring your attention to it. All right. And for the next lecture, we will start talking about the Joule experiment, the Joule-Thomson experiment, where we'll see how scientists set up an experiment to keep the internal energy of the system or the enthalpy of the system as constant. So we can measure the relative change of volume versus temperature or pressure versus temperature when keeping these energies at constant. And then we'll do a little bit more math together in like how these terms are connected. Just keep in mind, even if we're doing all these math, the whole purpose of thermodynamics is we're trying to solve for relationship between thermodynamic functions so that when scientists are doing experimental measurements, we can do as little experiment as possible because we know the relationship between these properties. All right, if we don't have any questions, I'll end a little bit early today, and I'll see you on Friday.